Dear colleagues, my name is Alexey Gunya. I'm an aspirant from the Lebedev Physical Institute in Moscow. My presentation is dedicated to the problem of the mechanism and cosmic ray origins, the proton accelerations in the AGN. The question of the origin of ultra-high energy cosmic rays has been open for more than a half of century. The sources and mechanisms responsible for the emergence of cosmic rays at the extensibilities. It's assumed that the scenario of stationary acceleration by an electric field in the vicinity of AGN is the most energetic and efficient of all the existing ones. For AGN, the acceleration process begins, for Proton, in the magnetosphere and ends in a relativistic jet. The protons is interesting because it's about 90% cosmic rays, and because it experiences slower losses during accelerations than, for example, an electron. So, the proton energies have limited value for inactive nuclei, active nuclei, and intergalactic medium. Ultra-high energy protons can exceed the energy threshold where the dissipation of relic photons has significant effect. The main sources of cosmic rays are the Sun, the pulsars, supernova, gamma-ray bursts, and of course, AGNs, which one of the greatest interest in terms of ultra-high energy cosmic rays. Various acceleration mechanisms can be implemented in cosmic ray sources. Electromagnetic stationary acceleration, turbulent MHD acceleration, supernova shock waves, and very popular reconnection of magnetic field lines. The main instruments for registering cosmic rays are, for example, the Cherenkov telescope has MAGIC, Veritas, and the orbital Fermi, of course. But what is an active galactic nucleus? This is a special state of the galactic nucleus. This is a natural cycle in the galaxy's life. The activity of the nucleus with plasma relativistic outflows is preceded by an intense accretion of the central black hole. One of the models predicts that the active state of the nucleus is a regulator of the intensity of star formation in the galaxy. But what process is responsible for the transfer of rotational energy of the black hole to matter and eventually to the jet formation? The most successful mechanism for explaining this is the Blandford-Znajek process. In a turbulent process of plasma accretion, the plasma magnetic field lines are moved to the black hole ergosphere. The rotation of the black hole also causes the rotation of the magnetic field lines. Stored enormous rotational energy is transferred through the rotation of the magnetic field lines, which leads to the appearance of apolar electric fields. It's very similar to the dynamo machine concept. Eventually, the accelerated photon in the magnetosphere shifted towards the light cylinder by a centrifugal force. The light cylinder is an imaginary surface where the linear component of the particle's velocity tends to the speed of light. The whole process is possible for a rotating black hole at an angular velocity which directly affects the angular velocity of the magnetic field lines. As a result, we get the total limited energy extracted from the rotation of the black hole. The acceleration of the proton begins in the innermost accretion disk regions during turbulent accretion. Next, the proton receives the bulk of its energy in the region of the magnetosphere. Part of the protons, after acceleration, can leave the AGN vicinity. However, most of all continue to accelerate in the jet. After gaining maximum energy for the cosmic rays level, proton leaves the jet. The main part of the jet plasma collides with the cloud and forms a reverse current, thus closing the circuit. The magnetosphere has a structure of an electromagnetic field, which in particular form the trajectory of particles accelerated towards the light cylinder. The magnetosphere is made up of toroidal and poloidal magnetic field. The toroidal field becomes much larger than the poloidal one in the region of the light cylinder for the system with AGN. Inactive nuclei have a very weak toroidal field. The rotation of the poloidal magnetic field produces a polar electric field. The topology of the magnetic field lines of the magnetosphere has a helix-like structure. As well as in the magnetosphere, the magnetic field of the jet also has a helix-like structure, consisting of longitudinal and toroidal fields. The electric field in the jet has a radial component. The accelerations of proton in the magnetosphere is described by a system of differential equations of motion in a spherical coordinate system. Since the motion of the proton is also described by inertial forces, the acceleration is described by a purely kinetic approach. The equations contain the numerical parameters of the magnetic field and magnetization, which is analogous to the Mitchell criterion for magnetospheres of neutron stars. The magnetization parameter describes also Hill's criterion, according to which a particle in accelerator with a magnetic field gains a minimal energy before leaving it. The acceleration in the jet is described by equations in a cylindrical coordinate system. There is also a kinetic approach. The equations contain the numerical parameters of the magnetic field and the electric field value. From the solution for the magnetosphere, it can be seen that the proton gains the main energy in the near-surface region of the light cylinder, the thickness of which is the same for the case of inactive and active galactic nucleus. For active and inactive nucleus, we have different dependence of reaching the maximum energy. The distribution functions also show that there are much fewer high-energy protons for AGN, which actually explain their rarity. With further acceleration of a proton in the relativistic jets depending on the parameters of the electric and magnetic fields, 3 different scenarios are possible. In the first scenario, the electric field amplitude is large and the proton is accelerated in the untrapped regime, gaining maximum energy and going beyond the jet. In the second scenario, the parameters of the electric and magnetic field approach each other in values, which leads to the trapped regime, where the proton oscillates between the axis and the boundary along the jet axis. The third scenario is non-accelerated. Here, the proton has only an initial energy with insignificant oscillations along the jet axis. For the magnetosphere, depending on the nucleus activity, the proton can eventually take on different energy values. For an inactive nucleus, we also have corresponds to the data obtained at Hess telescope. Also, we have energy for an inactive nucleus and total energy for any AGN. The black hole voltage, relativistic jet voltage, and energies are estimated for all proton acceleration regimes in the jet. Voltage is an important feature that determines the acceleration regime. If the voltage of the black hole is greater than the voltage of the jet, then the proton is accelerated in the untrapped regime to the maximum energy. Otherwise, the proton will be accelerated in the trapped regime. The result of various scenarios of proton acceleration can be represented as follows. And the most powerful and efficiency cosmic ray acceleration mechanism is the stationarity acceleration by electric fields in jet and magnetosphere. Bulk of the energy proton achieved near the light cylinder surface in magnetosphere. Because of the special relations between toroidal and poloidal magnetic fields, the total energy doesn't achieve by protons in the center black hole magnetosphere. We have 2 cases for no AGN and AGN system energy achieving. The proton acceleration occurred by the different scenarios in the relativistic jet. And a bonus, the energy generated by a black hole for the case of inactive nuclei is only partially achieved in the magnetosphere by proton. In the next work, we will consider the possibility of adding the maximum energy by proton in the Fermi bubble. More details about acceleration by a proton can be found in these works. The calculations for this project were also carried out on the Amazon servers. Thank you for attention.